Yeah, so I'm going to tell you about neural autoregressive systems or models for many-body physics. And these are the institutions supporting my research. So let me start with the question, what are autoregressive models? And I'm going to start introducing them in the context of probability. So what are probabilistic autoregressive models? So the term autoregressive originates from the literature on time series, where these models are such that observations from previous time steps are used to predict the value of function at the current time step. Okay, so that's very broad. But in the context of probability, let me just define a probability distribution over a variable sigma, where sigma is a vector of sigma I. Like you can think about them as spins, which take values 0, 1, all the way to d minus 1. And so you have this n spins if you want, and so you were defining a probability distribution over those variables. And the idea is that if you use the chain rule of probability, you can write down this probability of sigma 1 through sigma n as probability of sigma 1 times probability of sigma 2 condition on sigma 1 times probability of sigma 3 condition on 1 and 2, all the way to probability of n condition on all the previous spins. And then the autoregressive part is the fact that, for instance, for predicting the probability of sigma 3 depends on the previous variables in your vector sigma 1 and sigma 2. Okay, so that's kind of like where the names come from. And the idea is that if we want to specify this probability distribution P of sigma 1 through sigma n, so in a tabular form requires exponential resources, right? Because this is a huge table, and this is also true even if you want to specify, like, I don't like the conditionals, right? So it's an exponential resources that you want to avoid, right? Like when you're trying to model either probability distributions in real life in machine learning, or when you're trying to parametrize models in quantum many-body physics. And the insight comes from machine learning is that you can parametrize these conditionals, right? Like so instead of specifying all those conditionals in a tabular form, you impose a model, right? Like with some parameters theta, and then you basically compress or like restrict the number of probability distributions that you can describe. Okay, so that's the idea. So these probabilistic autoregressive models have certain advantages. So they can be exactly sampled in polynomial time if you have a finite number of parameters in the model. Computing the probability of a configuration of a given p sigma, it's efficient, is actually linear in the number of variables you have if you have a number of parameters that doesn't grow with the size of the system. They can be defined in any spatial dimension. Other important thing is they contain mean field theories, which are usually a good starting point in quantum many-body physics. For instance, you can describe this as a mean field theory in some limits. You can impose symmetries and other inductive biases, and so on. So I think that this set of advantages are very important when you're trying to model quantum many-body systems. They have a disadvantage, if you want, which I have a question mark there, because like some people don't think this is a disadvantage, but if you need expectation values or this distribution, it requires sampling, okay? And so, if, for instance, when you compute observables and grays, they come with an error bar. So that's not necessarily a disadvantage, but I'm just like thinking, for instance, if you're doing matrix product states, then you don't have this. But on the other hand, like these expectation values won't be biased by correlation effects because you can sample these models exactly. And so I think this is not necessarily a disadvantage. So these three properties and advantages that I highlighted here will extend and will remain true for autoregressive models of the quantum state. Okay, so I think this set of characteristics of these models are very important and very powerful. So, and I'm going to try to convince you that we can use these models to study many-body systems. So, and what's a canonical example is the recurrent neural network, which is very popular in machine learning. So recurrent neural networks are a set of machine learning architectures that are, where what we do is we parameterize the conditionals in the chain rule. So we're using this expression again, and what we're doing is that the recurrent neural net parameterizes each of these conditional in this decomposition. The building block of the RNN is a recurrent cell, so which I depict here. So it has 2 inputs, so this vector HN and this, if you want, spin configuration sigma and I, and then you send those through this RNN cell, and then this spits a conditional distribution. Okay, and the recurrent part of in the recurrent cell is this this relation here that I'm highlighting with my mouse. Hopefully you see it, and what you see is that the value of HN depends on the value of HN step n-1, as well as the, if you want, the spin configuration. And there's just f is just a nonlinear function, and the parameters of the RNN are those w and vector b, so they're matrices, right? And then out of this HN, you can compute the conditional probability by using some other nonlinearity, for instance, the so-called softmax. And so that's how you get these conditionals. I guess the dependency on the previous unseen spin configurations comes through this HN, right? Like, and then so you're able to somehow parameterize in a simple way this conditionals. The sampling, as I said, is efficient. You can do it in polynomial time. So you sample each conditional, and the input, like the outcome of each sampling of the conditional, you source as the input of the next call in the RNN cell. Some other interesting properties of the RNNs is that they're universal function approximators. So this has been shown in this paper from 2006. And some RNNs are even Turing complete, as proven in this paper in 1992. So they're very powerful. I was talking about neural autoregressive models, and I just mentioned one, which is one that I'm going to be using in this talk, but there are many more, and the list is very long. So I'm going to just flash a couple. So the transformers, which I used to in this talk, neural autoregressive density estimators, which are also very powerful, autoregressive flows, pixel RNNs, pixel CNNs, WaveNets. There are many, many. So these are just the names of some of them, and they're powerful in different situations, different scenarios. So how are these models used in machine learning? They basically, a popular application is neural language models. So in which a neural network is modeling language, right? Like, and they're commonly used, for instance, in machine translation, in text completion, language modeling. And in those cases, what you do is you model the probability distribution of an output text given some input text, or the probability of a sentence in English given that you saw the sentence in Spanish. So this is very useful for translation. Okay, and so here's one example: this text generation using neural autoregressive language models. So in here, what you do is you model the probability of output text given some input text. And this is an input I sent to a website. It's called talktotransformer.com in September last year. And the input was quantum supremacy has been. And then this thing completes the text, right? Like, and what this model completed was seen in a series of experiments carried out at the Joint Quantum Institute in Cambridge and the University of California, Santa Barbara. So this was even before the Google supremacy experiment and so on. So it's a funny, in retrospective, that somehow this is already in the news for a long time, and then these machines, when you train them, they pick up all this details and information, quantum effects and so on. So this is a funny example, but demonstrates how powerful these models are. They reproduce correctly strong correlations in the data and in the language, which are usually power low. So why to use these machine learning models for physics? So one example is the dimensionality of the, like, common dimensionality between quantum systems and neural machine translation, for instance. So as we know, in quantum many-body physics, for spin-1/2 systems, the size of the state space grows exponentially as 2 to the n, where n is the number of spins. This limits our ability to perform computations, and And but on the other hand, language translation models live also in very high dimensional spaces, right? Like, so for instance, you can imagine the size of the machine, the like state space of a language model is the vocabulary size to the maximum length of the sequence. So if you have a vocabulary of 8,000 words in a paragraph with 100 words, then the size of the state space is 8,000 to the 100. So it's a very large state space as well. Okay, so that's a commonality we have with these problems. The other commonality is correlations and symmetries with similar structure. So we have high dimensionality, but we also have critical correlations, for instance, in natural language, natural images, and so on, which are very similar to when we study, for instance, critical systems, okay, in many-body systems and so on, where you saw all these power law correlations. Machine learning data is also, I mean, it has a big bunch of symmetries that are also common to many-body systems, like translation, rotation, reflection, and this drastically improved the sample complexity of the machine learning algorithms, the same way we use the symmetries to improve the accuracy of calculations in many-body physics. So the hope is that I mean, when we parameterize these models, then we cannot cover all probability distributions, but hopefully the set of probability distributions that we can compute are useful for some machine learning tasks, but also for many-body physics. Okay, so and I'm going to try to convince you that this is true. So I'm going to talk about three things. So first, I'm going to introduce a probabilistic simulation of quantum mechanics, which is a version of quantum mechanics that uses mostly probability. And I'm going to show you how to, or one application of that, which is reconstructing quantum states without regressive models. Then I'm going to talk about simulation of quantum circuits using just probability and autoregressive models. And finally, I'm going to mention briefly recurrent neural network wave functions. Okay, so that's what we have in mind here. So how do you define probabilistic simulation of quantum mechanics? So can you even do that? And this question has been there for a long time. So Feynman in 1981 has this paper that motivated the field of quantum information and quantum computing. And he's talking about simulating physics with quantum computers. So in that talk, he asked the question, can quantum systems be probabilistically simulated by a classical computer? And he answers the questions as a no, if you want to do it exactly, right? Like so, and this is still true today, and it's fundamentally linked to the notion of quantum speed up, okay? So the conclusion is you cannot use just probability. But then we, like more recently, we asked the question, can we, okay, we can simulate this quantum states and dynamics using probability, but can we do it approximately? And can we reformulate this question as a machine learning problem? And so let me go quickly through it. So usually a quantum state is represented by a density matrix, which describes the statistical state of a quantum system. It's just a positive semi-definite Hermitian operator of trace 1 acting on this Hilbert space, right? And that's how we do it traditionally, but we can do it alternatively. Like we can write down quantum mechanics with just probability of the quantum state with just probability. And to do that, we use positive operator value measures, or POVMs, which are measurements that you can go and apply on the lab. They're described by the set of operators M. They're positive semi-definite, and they're, if you want, they span the entire Hilbert space in some cases, right? Like the idea is that then there's Born rule, right? Like which relates the probability of measuring some outcome A to the quantum state rho through the operators that you measure MA. And this is, if you want, the link between quantum theory and experiment that Born basically came up with. Now, if you consider a set of informationally complete measurements, then that means that the measurement statistics PA contains all the information about the quantum state. And so that also implies that the relation between rho and probability distribution can be inverted. And that's what we apply here, right? So instead of specifying the state as a density matrix, you can specify it as a probability distribution of an informationally complete POVM. And so what we do is we construct POVMs and then we model the quantum state using this probability distribution P. So there's some graphical notation here. Basically, this probability distribution equals to the density matrix times the measurement, and then you trace. So this is tensor network notation. So it's not very important right now, but the crucial thing is that if you have informationally complete measurements, you can then invert the Born rule, which is this expression here. Okay, so you can write rho as a function of this probability distribution in terms of the measurements. And then everything about quantum mechanics follows from that, like unitary evolution, the Schrödinger equation, Lindblad dynamics, measurements, and so on. So here I have the example of the Liouville von Neumann equation written in terms of probability. Okay. So that's the most, like, if you want the important message here. So what we did was, okay, we're going to parameterize the statistics of the measurements, and then we invert this this relation. And what we do is we take this probabilistic models, this neural autoregressive models, to parameterize this distribution PA, and then we have a model for the density matrix in terms of those distributions. As we said, we use these models because they allow for exact sampling and for a tractable computation of probability of any configuration A or sigma. So let me give you one example so that we can learn quantum states from measurements. So kind of like a quantum state tomography in this language. And why we did this, because we need to go beyond standard quantum state tomography, because the size of the systems that we're able to, or that people are able to prepare, are just going beyond, well beyond what traditional quantum state tomography can deal with. Like here I have examples on cold atoms and trapped ions. So we need to try to improve that, and that's what we did in this paper, for instance, with my collaborators. So, and here are reconstructing ground states of local Hamiltonians from data. And this is using a recurrent neural network. And so here what you see is the reconstruction of some correlation functions on the ground state of the transversalizing model. So here you see the expectation value of sigma x as a function of psi I, and this is two-body correlation functions. And as you see, the reconstructed state is very close to the synthetic state. So this is numerical simulations using DMRG on 50 spins. Here below, what you see is a two-dimensional system. Is the Heisenberg model on the triangular lattice, which is very nice because it highlights the fact that so this model has, if you want a complicated sound structure in the computational basis, but nevertheless you can represent its ground state with just using probability, right? And you achieve like a good reconstruction, as demonstrated like in the similarity between the correlation functions of the simulated state and the reconstructed one. So so this is all through probability distributions and recurrent neural networks. So we experimentally demonstrated this recently. So we took, we prepared a GHZ state with 3 qubits on an IBM quantum computer, and then we were able to reconstruct this density matrices both with traditional maximum likelihood estimation and with a model, a neural autoregressive model called the transformer. So this is in this paper here with Cornell. We also did a simulation of quantum dynamics, right? Like, so this is all based on data for a fixed quantum state, but we also wanted to explore if we can do real-time dynamics or simulation of quantum circuits using these models. And this is what we did here. So when you're doing unitary evolution, what you do is you transform the density matrix through a unitary matrix U, and then you get your time evolved or unitarily rotated density matrix. So if you translate that into a probabilistic setting, what you see is this, right? You go from some probability distribution P to a rotated probability distribution PU through a matrix O. And these matrices are very interesting. They're similar to probabilistic gates, except they're not stochastic matrices. They're so-called somewhat stochastic matrices or quasi-stochastic matrices, and because they can have positive and negative elements, but the sum over the columns adds up to 1. So they're very similar to stochastic matrices, and so the evolution is very similar to, like, say, Green's function Monte Carlo or Markov chain Monte Carlo, where this probabilistic simulation is almost classical, but not quite, because this matrix has a sign, so it induces a sign problem in the simulation. But we can do it approximately, right? So a quantum circuit and the simulation we perform is we start the quantum device in a simple product state. We apply a sequence of simple unitary matrices, and then we obtain the result. And this translates, so in the usual language, it's this thing here. So a set of unitaries applied to a quantum state. And then this probabilistic setting is you start with an initial distribution, you multiply it by this operators O, which are quasi-stochastic matrices. And so we did this. So how can we do it, right? So what we do is let me show you how to do it by applying one gate. So you start with the initial probability distribution, you apply this O, and then you get this output distribution PU, like the rotated distribution. So we cannot do this because these are exponentially big. And so what we did was introduce a model P theta, which is going to model this distribution. And we can compute a divergence between this exact distribution and the P theta. And then we found a way of minimizing this distance, okay? So we basically computed the KL divergence between this model and this distribution, and it is efficient as long as the gates are local, okay? If the gates are non-local, then this is very hard. But if we use local gates, as is the case in a real quantum computer, then you can do it. So we do that by computing or by producing an estimate of the cross entropy, and we minimize it, right? So this is an expression of the simplest implementation of what we did, but we do better. We introduce variance reduction and many more strategies, and you can see it in this paper. So as for one gate, if you want to apply multiple gates, then you have to do a little bit more. So you start with P0, and the idea is you want to get to P3, and then you just have to repeat this procedure on and on. The problem with this is errors. So when we do this minimization is not perfect. So you start accumulating errors, pretty much like what happens in a real quantum device. But the idea is that in the end, you still get a good approximation of the probability distribution that you're trying to approximate. So these are the results. So we prepare the simple states, the GHZ state, and the linear graph states. And let me show you how this looks like in simulation. So this is for the application in the first row for the application of two gates. And this is the KL divergence between the two distributions, between the exact distribution and the model distribution. As you see, as we train, the scale divergence goes to zero exponentially fast, at least at the beginning, and then it saturates. And when you apply the second gate, you again see an exponentially decrease, and then it levels off. Same is true for the classical fidelity between the two distributions, or the classical infidelity. It goes exponentially fast to zero, and then it levels. And the same is true for the second gate. This is a norm between the distance between the two distributions, and then it goes exponential. And then this is the true fidelity again, the quantum fidelity between the quantum states. So it goes exponentially fast to zero at the beginning, and then it levels off. The same is true here. So here we have just the application of this control Z gate, and the same is true. This is based. Yeah. Sorry?
5 minutes.
Okay. So let me go quickly through this. So now we scale this to a large number of qubits, up to 60 qubits. And what we see is as we grow the number of qubits, the fidelity or classical fidelity goes down as expected because the error keeps accumulating. And this is results for the graph state with 16 hidden units in the model. So we make basically a model that is powerful, but not quite. And then as we increase the power of the model to 32 hidden units, the simulations tend to improve, okay? So that's the simulations. And then to conclude, let me go through last part, which is recurrent neural network wave function. So we were simulating these quantum states by using probabilistic representation. And that has advantages, but also has some drawbacks that I didn't have time to explain. But then we took a look at how about we do direct simulation of the quantum state. And this is work by my student, Mohammed Kibat Allah, that was published recently in Physical Review Research. And so what we did was we took the recurrent neural network and we basically generalized it to the quantum state, right? And what we do, instead of parameterizing just conditional distribution, we parameterize somehow like a conditional wave function, right? Where basically what we do, instead of just outputting probability, we output local phase for each spin, and then we sum over the different phases that this model outputs, and then we construct the wave function out of the square root of the probability part and e to the I the phase part. Okay, and then we took a look at several systems. So we took a look at the translucid model in 1D and compare with DMRG, which is the gold standard for like simulation of many body systems in 1D, and even in 2D in some cases. And what we see is the energy is just it reaches low values and also is low variance. We also took a look at the J1, J2 model in 1D, and we also, again, we find decent energies, very accurate solutions. Here are, like, for instance, for the translucid model in 1D, results comparing DMRG correlation functions with the correlation functions we find with our recurrent neural net approximations. We compute the second Renier entropies for n equals 80 and compare again with DMRG. We find very good accuracy if you want, and the calculation is very fast. These Renier entropies, and they have very small error bars, which in some cases, in some other wave functions are very tricky. You have to apply different functions, different tricks to improve. So we apply several and we introduce several symmetries like spin inversion, mirror reflection, and conservation of magnetization for like, for instance, for the J1, J2 models. We can also impose different Marshall signs and so on. The most exciting part is that we can also deal with two-dimensional systems, and here we compare like DMRG one-dimensional RNN with two-dimensional RNN, and what we found is this is for a 12 by 12 system on the translucid model in 2D. And what we found is that this 2D RNN that my student introduces really, really accurate. I mean, all results are very accurate. So red is DMRG as they're all very, very good. And we compared it with Pixel CNN from Giuseppe, actually, and they're all very accurate in the end, but we managed to see a little bit of an improvement with respect to the other systems. And with that, let me conclude. So what's in our neural autoregressive toolbox? So I showed you how to do quantum state reconstruction with recurrent neural nets and with transformers, which we recently demonstrated experimentally with a group at Cornell. We demonstrated we can simulate quantum circuits. This is all based on probability only. Then we extended this to recurrent neural network wave functions. We can compute ground states. We tried this transfer learning based on physical principles with Isaac Tamblyn at NRC in Ottawa. And more recently, we were exploring neural simulated annealing. This is coming soon, where we, using this simulated annealing based on neural networks, we find better solutions for Sherrington-Kirkpatrick string class problems, which are better than quantum Monte Carlo and more. And with that, I'd like to conclude and thank you everybody for attending and the organizer for the invitation.